Okay, so this is part 2 of 1.2, and we're going to go ahead and look at graphing and finding what's called local extrema or local mins and maxes, or relative extrema, it's often called. So we're going to start with this function in example 8, x to the fourth minus 7x squared plus 6x. So go ahead and enter that into your calculator, because I want you, again, to do this with me. And then once you got it entered, you go to zoom, and we're going to go zoom 6, zoom standard. I usually just press the 6 button. And I can see here, I'm going to show a couple of extrema, but there's also one I cannot see. So here I've got where it kind of hits this top, a relative max. I have a relative min here, and then there's one down here. So since I can't see that, I'm going to adjust my window. And I do not want to do this with zoom. It just leads to too many problems. So I go window, and all I'm going to do is change my minimum y to -20. I think that'll catch it. Nope. Okay, -20 wasn't big enough. Let's go -50. There we go. Now, where I've got circled is all off because I changed my zoom, and that's fine. I can still see what I need here. I got a minimum here, a maximum here, and a minimum there. In order to find those, I'm going to go second calc or second trace, and I'm going to go to let's do the minimum first. So it wants a left bound. I think -4 will do it for me. I'm just going to enter it. That's on the left side, right bound. I'm going to go -1. Again, you can scroll over with the arrows, or you can enter them. So yes, I have a minimum between there. My guess is -1. And I can see that my minimum has an x coordinate of -2.06, if I round that, and a minimum y coordinate of -24.06 as well. Okay, to find my next one, I'll find the maximum. So I'm going to go second calc again, and I'm going to go to max. My left bound needs to be on the left side of that max. My right bound somewhere on the right. I like to go before it hits the next one. Guess doesn't really matter. You can put it close if you want, but as long as you're in the right range, you're fine. The maximum has x coordinate of 0.456 and a y coordinate of 1.32. Again, if we ask where is the minimums and maximums, we're looking for the x coordinates. It's not random. It's not pick a coordinate. It's where are my local extrema? Where is entered by my x coordinates? What is my minimum value would then be my y coordinates. Okay. And we've got one more minimum to identify. I'm going to make sure I get past that other one. If your range included something over here, if you had your thing too far over, like over here, it'll give you something way down here because that value is lower than here. So it's important that we have our windows here where this is the lowest point in the region. And my minimum here is 1.60, -1.77 for a y coordinate. So that is finding local extrema. You're going to do it with the calculator. There's a way to do it without the calculator. It involves calculus. Guess what? You don't have to do that this year. And I hear all kinds of hoorays. We're going to check our graphs for symmetry. So I'm going to put in 3 different functions. And because they're colored, this is really handy. This is why I really like the ones with color screens. So because I've got a colored screen, I'm just going to enter all 3 of them at a time. If you don't have a colored screen, you want to enter all 3 of them, you could. And this you can turn your graphs on and off by having anything with the equal sign darkened is on, anything without it darkened is off. And again, I got a fraction for this third one. Yeah, I think I'm going to go to Zoom 6 again. I think that'll kind of fit all of them. Okay, so the first question is symmetry. So I can see there's a couple of different types of symmetry. There is y-axis symmetry, or even vertical symmetry. Okay? And if you have y-axis symmetry, which this blue one does, that function was, okay, we'll do it in blue. Y equals x squared minus 3. Y-axis symmetry we call even functions. The red one does have a symmetry to it, but it's not on an axis. So it has symmetry, but it doesn't have one of our primary types. For even functions, f of x should equal f of negative x. So what does that mean? Means f of x is this. F of negative x means I plug negative x in for x. Well, that does equal, when I square a negative, I get a positive. So hey, those are equal. That is even. My black one, I'm going to use purple for, actually appears to have origin symmetry. So this is h of x equals x cubed over 4 minus x squared. Origin symmetry means if I pick a point and I draw a line through the origin, it should connect to the other side. Pick a point here, so say -2 and +2. And this should actually be here. I draw a line. It's a little hard to make straight lines here. But that point goes to the origin. It cannot, if I shift this up one, it's not origin symmetry. And for odd functions, h of negative x should equal negative h of x. So what does that mean? H of negative x, I plug in negative x for both my x's here. Negative h of x just means I tack a negative on the front. And I'm going to check if these are equal. Negative x cubed, negative x times negative x times negative x is negative x cubed. 3 negatives make a negative. Negative x squared is positive x squared. And is that the same as what is on the right side here? Yes, the negative can be in front, the top, or the bottom. There's one negative there, so that is an odd function. Okay, we've talked about asymptotes already. And I'm going to introduce you to limit notation a little bit as we discuss asymptotes. And then we'll talk about end behavior. Because end behavior can also be shown with limit notation. And a limit is a new thing. We're going to study it in more depth here, I think next week. But a limit is telling me, where is y going? Where is y going as x goes towards this point? So I'm going to clear all of these out and put in a new function. And we've talked about rational functions. We learned about them last year. We know they have vertical and often horizontal asymptotes. Oops. So remember, my vertical asymptotes are found by figuring out where my denominator equals 0. So ultimately, I'm looking for, where does my denominator equal 0? Kind of looking like -1 and 2. Sometimes that could be helpful. So I'm checking here. Denominator 0. And I'll factor x plus 1, x minus 2. Because I knew -1 and 0, x plus 1 equals 0 or x equals -1. Or I was at least taking a guess based on looking at the graph. And when I move 2 to the other side, x equals 2. 1 times -2 is -2. 1 plus -2 is -1. Yes. My vertical asymptotes are at -1 and 2. We'll talk more about finding the horizontal in the future, but here it looks like it's 0. So let's talk about limit notation. And we're going to talk about writing these things, and I'm going to use red now to write these limits. Okay. So for this asymptote, limit as x approaches -1. Well, here I have a left. It's going a different way when I'm looking at it coming from the left, coming down this branch. So I'm going to have to write this in separate ways. And this was of, I'm just going to use y1 because that's what I did it as. Wish they would have used f of x so I could write less. As I come to it from the left side, I'm going to -infinity. So it's going infinitely down. As I come to it from the right side, however, this little plus sign up here indicates that I'm coming along the right side, -1. That is positive infinity. If I just ask you about the limit as x approaches -1, because as it approaches from the left side and the right side, that's not the same, that limit does not exist. And this terminology is important. If you haven't seen Mean Girls, the limit does not exist. If you have, you probably know what I'm talking about. I abbreviate does not exist with capital DNE. I don't like to write, so it's a pretty standard abbreviation. I've also here got another side though. So I need to show my other asymptote. I don't usually show the single one. I usually, for asymptotes, we just show the one. A lot of times you'll write the actual function in here, but if they give it as f of x or g of x, you can just write f of x or g of x. This one, as I come at 2 from the left side now, as I'm drawing it in, that's going down to -infinity. as I come at 2 from the right side, I'm looking at where is my y going. Limits are about where does y go as x gets closer and closer to this value here of 2. From the right side, y is going to infinity. I'm also often interested in what we call end behavior. End behavior is where does my graph go? What's my y value going towards as x gets really out towards its horizontal ends? So as x approaches negative infinity, that's way over here, way over on this way left side of the graph, that appears to be getting closer and closer to 0. As x approaches positive infinity, way here on the right side of the graph, it also appears to be going to 0. Okay? So end behavior can be a very interesting thing. Very important for us to look at. Okay? So we're going to match up some functions with graphs using end behavior. And I'm going to go to a whiteboard and just draw out my graphs, and my functions. And they use y for all of them. I'm not going to. I'm going to say f of x equals 3x over x squared plus 1. G of x equals 3x squared over x squared plus 1. We're going to think about end behavior with these, and try to compare the graphs without using a graphing calculator for these. Okay, so when we're matching graphs to functions, we want to try to do that without our graphing calculator. And if you can't, so here's the last one is k of x, then start checking with your graphing calculator. Now, all of these are over x squared plus 1. Here's a little hint on that. X squared plus 1 can never equal 0, so none of these are going to have asymptotes. So I've got here graph A, B, C, and D. So as I look at this first one, A, I'm going to think about simplifying. Because I'm thinking about end behavior, if x is like 10,000, 10,000 squared is 100 million, does adding 1 make much of a difference? Not really. So I'm just going to kind of look at this part. And when I reduce that, I get 3 over x. 3 over x as x gets really large goes to 0. Or 3 over negative really large x would go to 0. So this one is probably D. That one makes sense there. Again, the plus 1 doesn't matter. So that becomes 3x squared over x squared. As I'm going towards my ends, it goes to 3. This one looks like it goes to, they've got dashes on the one in the book. Looks like it's getting close to 3. So that's C. Right here, when I reduce that, I get 3x. This kind of looks like y equals x. Looks a little more like an x cubed, just because of how this is scaled. But this is B. That one you could also use process of elimination on. And here we've got 3x to the 4th over x squared. That's 3x squared. Oh, that one's definitely there. So A. If you weren't sure on B, thought that looked too much like a cubic, it kind of does. The thing about these is we're looking at end behavior, so you kind of have to ignore this chunk in the middle that looks a little funky. This one, y equals 3, horizontal line. That's what it's getting close to once I get away from that middle. 3 over x. This middle doesn't look really like 3 over x, but the ends do. So checking end behavior can be very powerful for classifying graphs. Okay, that is the end of the lesson for 1.2. And you may work on your problems.